Okay, our first and most common cycle that we are going to deal with is going to be a power cycle. I say most common just because when we think of the lights around us that are power that we have to run the computer that you're looking at or the phone that you're looking at, a power cycle is what needs to happen. Okay, so we're talking about here in a power cycle, we're talking about a power plant. We're talking about an engine. Okay, we're talking about those kind of things. And when we draw our cycles, we're going to draw them in a very interesting format here that you're going to see. So we're going to put, this thing is going to look like this. Okay, these pieces right here, these are thermal reservoirs. Okay, that's both a thermal reservoir. And what we're saying it is going to be a place of constant temperature. Okay, so the one up here is going to be a high temperature reservoir or a hot reservoir. And the one at the bottom is going to be a cold temperature reservoir or a low temperature reservoir. Now, when I say cold, I mean it's cold relative to the hot temperature. I might have 1,000 degrees Kelvin. I might have 1,000 degrees Kelvin, and I might have cold is going to be 900 degrees Kelvin. That's still very warm, but it's cold relative to the high. Okay, and in here, what I'm going to draw is I'm going to draw a cycle. Okay, here's a cycle. I'm going to draw a circle here. Just say there's a cycle that's happening inside of here. Because what a cycle requires, a power cycle requires, is I must give this cycle some heat. And so here I come in here. Qn is coming in from that high temperature reservoir. It's providing heat to my cycle. Okay, in some places it's providing heat to my cycle. Okay. In a power plant, that's because we burn coal or we burn natural gas. We're providing heat. Okay. In your engine, in your car, you're burning gasoline for this to happen. That's what's going on. And what that is going to do is it's going to have this cycle is going to produce some work, out. You know, it's rotating something, producing power, producing energy. We can look at these in different ways. And it doesn't convert all of the Q in into power out. It does going to also reject some heat out of the cycle. Not all of it gets used. Okay, we'll explain why this is the case and how this occurs in chapter 5 when we will re-look at these very things. Okay, but you just need to know right now, you have some heat coming in, it produces some work out, and it has to put some of that heat out the other end. Okay, now, if we look at this power cycle, we're going to say that for the cycle, the change in energy for the cycle is equal to the summation of the heat transfer for the cycle minus the summation of the work for the cycle. Okay, that's what we just talked about. And we said the summation of the energy is going to be the internal energy only, and that internal energy is going to go to 0. So we are going to just be left with the heat transfer of the cycle and the work of the cycle. So what do we have here? 0 is equal to, well, let's see, what do we have for the cycle? Basically, we're going to be looking at if my system is going to be this. My system is my cycle, and I'm saying, well, we have coming in is Q in. So I'm going to say Q in, and going out is Q out. So Q out. You know, I made sure I made my sign conventions right. Coming in is positive, going out is negative, and that's going to be my heat transfer. And then minus my work. I only have one work, and it's going out, so that's going to be positive. And so I'm going to put work of the cycle. Now, what I like to do now in this equation is I like to put magnitudes symbols around here because we're going to be doing some mathematical or algebraic moving around. And I want you to understand that the signs now, we're saying if we put the magnitude of the heat transfer in and the magnitude of the heat transfer out and the magnitude of the work, we've already taken care in this thing, we've already taken care of the signs the signs here, this is a positive sign. We've already taken care of all the signs. So when any manipulation we've taken care of about this algebraically, we don't have to worry about the signs because we're going to put magnitudes. We're going to put magnitudes into this equation. I hope that will make some sense here in a minute. Okay, so what do I get here? I get that the work of the cycle is going to equal Q in minus Q out. Okay, it's easy as that. I can find out how much work my cycle produces by finding out what is the magnitude of the heat coming in minus the magnitude of the heat going out. I know how much work my cycle produces. Okay, now what we're going to do with the power cycle is we wanted to calculate what its thermal efficiency is. Thermal efficiency, and we're going to call that thermal efficiency eta. This is a eta, which is just a fancy N there. Maybe I need to make it a little bit more looking like an N. Eta. And when I think about thermal efficiency, what I'm going to think about in words is what you want over what you have to give. Okay, efficiency is what you want or what you have to give. Sometimes I just say want over give. Okay, so let's talk about thermal efficiency for this power cycle. What do we want in a power cycle? Well, we want to produce work. That's what we want to do. So we want work cycle, which is the same thing here as my work out that I have up here. What do we have to give for that to occur? Well, we're giving heat to this cycle for that to occur. So this is going to be Qn. All right, and so I'm going to put their magnitudes here just so I know this is all correct. And I can say, well, look what work of the cycle is equal to. I have this written here. I can also write this as Qn minus Q out all over Qn. Okay, that's another way to write it. Or I could say, you know what, just looking at this, I have a common denominator, I have a denominator here, I can do a little bit of work with my fraction. This is going to be 1 minus Q out all over Qn. Now I hope you see now why I'm putting magnitudes, because sometimes students don't know about this negative sign here in this word. They think, well, does this negative sign apply to the sign convention of my heat transfers? Well, no, we've already taken care of it. So we put this magnitude symbol on it, so I know I've already taken care of that. I'm just manipulating the equation. If you plug in the magnitudes of Q out and Q in, you're good to go. Okay, so I don't have every version of this on the equation sheet, but I think you should be able to, I have enough information on the equation sheet, you should be able to figure out what thermal efficiency is and all the different versions of the equations that you have here from this. Now what I want to express to you it's even more importantly here is that if I put this in a rate basis, if I put Q dots, if I put dots over this whole thing, okay, rates, come on keyboard, go away. It's the same thing happens. So I can put this in rate terms or in not rate term, in just looking at magnitudes, and I'll be fine. Because remember, a rate, this is going to be either, if I look at this equation here, it would be either in kilowatts all over, in energy, it's going to be kilojoules all over kilojoules, which is unitless, or it's going to be in kilojoules per second over kilojoules per second, which is also unitless. Okay, so that doesn't really matter there. The seconds are going to cancel out. It doesn't really matter. If they're all both on the same time scale, it doesn't really matter. So don't worry about whether you're doing this in kilojoules or, remember, this is going to be kilowatts over kilowatts. It doesn't really matter which way you're doing it. What you need to understand with this equation, efficiency is going to be a decimal number and it's going to be between 0 and 1. We can never have our efficiency be greater than 1. Okay? You can never get more out than what you put in. It's just not possible. It's just not possible at all. And so sometimes I want to put this into a percentage, and so I will take eta and I'll take it times 100% to get me into a percentage term. So I'm saying it's 90% efficient. It's 0.9 is eta, and take it times 100%, I have a 90% efficiency. Okay. Now, the couple things you need to know about a power cycle. This one is most important here. If you have a power cycle, you must have this thing here happens. You cannot go efficiency over the 1. Students all the time will give me efficiency over the 1. I'm like, what? Where did that come from? The second thing you need to know, you remember the first video where we had an unknown cycle with a lot of different processes in there? Well, if that unknown cycle has a net positive work, if it has a net positive work, it's got to be a power cycle. All power cycles have net positive work. So I'm just going to put this in here. Any unknown cycle, whoa, screen, whoa, what's happening today? Any unknown cycle, you have a little bit of delay. My computer is thinking a little bit. Any unknown cycle with network that's positive or out is a power cycle. Now you will see this on my practice exams when I put them out here. I've told a student that I get them out by Monday, and it's now Wednesday, and I haven't got them out. I'm going to work. That'll be my priority today. And I said that would be my priority on Monday. But man, this semester, this COVID-19 stuff, man, it's just a mess. Even if you don't have it, just working with all the situations. But anyway, you will see that I will often give a bunch of random processes, and I'll say, hey, is this a power cycle? And this is what you look for. You look for if there's net positive work coming out of it, it's a power cycle. Okay, so there we go. That's our ideas about power cycle. We will do some example problems of a power cycle in the in-person session of lectures. We can do a lot of problems about these actually. So look for that video on Friday to see some example problems.